Are you going to tell us about the production of negative ions in plasma?
Alright, yes, so good afternoon, ladies and gents. I hope you are still awake. So I will not talk about difficult things. I will keep it simple and not many formulas, and hope that you will not lose attention. So I do my PhD thesis in Marseille with a strong connection to Kazakh and within the Erasmus Mundus Fusion DC program, and I really thank my region and the CAA who gives me the financing. Okay, so let's start with the motivation. So as you know, fusion is one of the most promising future energy sources, even though you don't believe it's the most environmentally sustainable, but okay, let's move on. The DT is the reaction which is chosen in our Earth conditions for now, and ITER is currently being built in France. So what are the parameters that ITER requires, the technical parameters? So we need the temperature of around 10-20 keV, and as you know, plasma itself can heat by ohmic heating up to 1 keV. So basically it's not enough, and we need additional heating methods. So what are those? For instance, neutral beam injection. So you have low pressure, negative, just an ion source, alright, with a deuterium plasma, then the ions are being accelerated, neutralizing the gas target, and then they go into the tokamak, increase effectively the density, and we are fine. So, but the existing facility is really, really huge. It weighs more than 900 tons, and well, it consists of many other models like bushing, and then residual gas and residual ion deflector and calorimeter, and in the end it delivers 17 megawatts of power with 1 mega electron volts of neutral particles. Alright, that poses quite a huge question. So we need 1 mega electron volt of neutrals to heat ITER's plasma core, ignite the reaction. And basically we know that at this huge energy, all the positive ions that must be neutralized in the gas target would not be able to do so, because neutralization efficiency is 0. So we have to go with the negative ions. But the problem is that the required current of this negative ion should be really high, 50 amps. So the negative ion sources are not so far yet compared to the positive ion sources. So what does it mean? We need to develop a new large negative ion source. So in that concept is already developed in IPP Garching. So here you ignite the RF plasma. Here you have the filter field to get rid of the low energetic particles. You get the ion formation, negative ion formation here on the grid, and extraction. And this is all due to the help of the cesium which is deposited on this on the grid, on the extraction grid. However, cesium is not the best choice because it can diffuse inside the accelerator, and then it makes the beam collimation quite difficult, and there are many other issues that are not in favor of cesium. But currently it's the only way to meet all the ITER requirements. So what do? I do search for the alternative solutions to the use of cesium, and that might be quite useful for demo and maybe for ITER, we will see. But we aim for demo. Alright, I do it on a really small scale device. So as you see, it's hydrogen deuterium plasma, and we get the RF source here in the plasma afterwards from the Pyrex tube diffuses in the reactor chamber. We have the sample that we introduced here, the mass spectrometer. Alright, and here you see the power ranges, which are like low power, and these are the pressure ranges. We don't use the magnetic field, etc. So it's really a small device where you can basically yourself turn all the knobs and operate it alone. So that's why I like it. It's like this, and basically if you look at that window right here, you see a following thing. So you have a sample which is facing the mass spectrometer, and here you go. There is the Langmuir probe to control the plasma parameters that you have. So what is basically happened when we put our sample in the plasma? So we put it under negative bias. So there is an attraction of positive ions from the plasma towards the sample. Then they neutralize near the surface, interact, they get the additional electron, and then they are turned into into the negative ions, and they are attracted towards the plasma and towards the mass spectrometer, which is floating at ground. So in the end, you measure something like that, which is a negative ion distribution function. A number of counts is a function of negative ion energy. Quite simple. So here you see the experimental result, right there. And to understand basically what is happening inside our plasma, we try to do the modeling. So the first step for the modeling was that we took the stopping and range of ions in matter, the string program. It's a quite simple tool, but it's powerful and delivers us the distribution of neutral particles leaving from our surface. Okay, so it's not quite what we measure, right? So afterwards, what we need to take this neutral distribution function given by stream, then we calculate the transport of the negative ions in sheets between the sample and the plasma, then in plasma and the sheet between the plasma and mass spectrometer. And then we create a mass spectrometer model with Simeon, and we looked at the transport of ions inside the mass spectrometer. So in the end, by counting all this, we achieved a good agreement between the model function and the measured negative ion distribution function. Note that for these calculations, for string, we have taken 30% of hydrogen on the surface. Alright, and except for the modeling, the experimental results are presented here. So here you can see the temperature change of the highly oriented pyrolytic graphite, HOPG sample, basically a carbon sample. And you see the negative ion distribution function changing with temperature. So you see the negative ion yield is decreasing, and so you have a tremendous change in the form. Alright, so we try to understand what's basically happening. And for room temperature, we have seen that the 30% of hydrogen on the surface given by stream is quite well matching quite well the experimental results. However, for high temperature, we have noticed that the content of hydrogen on the surface has decreased. So basically we have done it for various temperatures, and it can be seen, well, so this is basically the conclusion. We have the decrease of hydrogen coverage on HOPG surface with temperature. So if you see, for all the temperatures, basically each point here is the integral under the curve. So we have the hydrogen surface decrease with temperature, and so does the yield. The yield decreases. We have tested other materials like boron doped diamond. Looks like that, and it has some maximum in negative ion yield at 400 degrees C, and then the yield decreases, and so does the hydrogen surface coverage, which is seen via the modeling. Then we have also taken the intrinsic diamond, which is normally non-conductive material, and we had some biasing problems before the high temperatures, and then we can surely see that the yield after 500 degrees C decreases, and so does the hydrogen surface coverage. So we try to understand why does it happen essentially. We have done some additional measurements with Raman spectroscopy, and we have looked at the ratio of sp3 over sp2 phases in this material. We have seen that for BDD, with temperature, it always increases, and with HOPG, it always decreases. Well, what are those magic letters, sp3, sp2? It's kind of confusing. So, not that confusing if you regard this famous diamond triangle. Here you have the pure carbon material with pure sp2 phase. Here you have the diamond material, sp3, pure sp3, and the hydrogen. Basically, we take our HOPG sample, which is pure carbon, which is here, we put it in the plasma. It appears something like, let us say here, because there are some defects induced in the sample by the plasma, and you have a mixture of sp3 and sp2 phases. And when you start to heat the sample, you move towards the virgin material. You heal the defects, and you rebuild the virgin material, and you notice that with heating up and with moving towards sp2, you decrease the negative ion yield. Okay, let's take our diamond materials, which is pure sp3. We put it in the plasma, it appears again here, and then we heat it up. So it starts moving, as Raman spectroscopy says there. Basically, we have an increase in the negative ion yield, and then a decrease. So somewhere there should be an optimal point for the negative ion yield, for the highest negative ion yield possible. So basically, the conclusions would be that we have seen that for HUPG, the highest yield was given at room temperature. However, for elevated temperatures, there was the intrinsic diamond given the highest yield. And the difference here is around 1 order of magnitude. Then we use the mass spectrometry to determine the hydrogen coverage on the sample surface, more or less to get an estimate. And then combining with Raman spectroscopy, we have seen that sp3 over sp2 phase ratio has changed while increasing the temperature. And this hence has changed the hydrogen surface coverage and the negative ion yield. And interplay between those three parameters is quite crucial. It's not so clear how do they interplay with each other. So basically we need to prove new materials to find this optimal state, and for that we need to understand the matter deeper. So the next steps would be we need to prove experimentally the change in hydrogen surface coverage, not just with the modeling, but we want to do the infrared spectroscopy and temperature program desorption spectroscopy to basically benchmark the modeling, or yeah, the other way around. And then we want to start probing the new materials, like lower function materials or large bandgap insulators, and then we want to try it in real life conditions. So we have a real negative ion source, which is being built in Kadarash, and it's equipped with the extraction device and accelerator. And hopefully, towards the third year of my PhD, it will be already done, so I can do some measurements there. And I would like to thank you for your attention.
One question.
So what do you know if the mechanics or the way in which the hydrogen bonds to the surface of the layer is different for sp3 versus sp2 materials? Is that what's causing the yield to change?
You mean the mechanics of the...
Yeah, the kind of the nature of the bonding of the hydrogen to the surface.
Right. If you regard just the mechanisms of interaction of positive ions impinging on the materials, there are only two mechanisms that are estimated, which are the backscattering and the sputtering. And then depending on the... So backscattering basically have the same ion coming back, and sputtering you get the ion heated out from the surface of the sample. The change of the sp3 and sp2 phases changes the ratio of the contribution between those two contributions, yeah, basically. And sp3, sp2 is just the way of kind of chemical connections of hydrogen between the carbon within the sample. So it's like basically the triangular connection with the sp3 and sp2 just in plane.
Yeah.
That's, as far as I know, it's that.
Another question?
Yeah. You obviously didn't work with cesium. It's not easy to work with, but do you know how your yield would compare to a negative ion source with cesium?
Yeah, that's a really good question, and it's a question that everybody asks. The thing is that we have not done any absolute measurements, and that's what are we trying to do now. There is an indirect method to calibrate the device that we have, and yeah, and the last step here is actually done for the direct calibration, because you basically extract the negative ion current, and you know how much do you produce. There you go. Yeah, and the good thing would be to put cesium in the device and to see like that. That would be like the best sort of calibration, but I mean, then you destroy your device for the future measurements, so it's not applicable. But okay, more or less, right now we are down by the couple orders of magnitude than with cesium.
Any other question? Just one.
I mean, you're just predicting the hydrogen coverage from the modelling. I mean, so
Yes.
how confident are you that that's reliable?
Let me say I'm not quite confident that the hydrogen coverage is the only parameter determining the negative ion yield. That's the thing. So that's why I want to do the experimental proof of the hydrogen surface coverage change with with temperature. So if that proves right, at least then I can say yes, the modeling is capable to predict that. But now I say it gives a rough estimate.
I mean, what would you... I mean, there's going to be varying changes with like the excited state of the incoming ions and stuff, which will have quite a large effect, I would have thought.
Basically what we assume that the effective cross-section of interaction doesn't change with the temperature. But if you account for that, then I mean, all the modeling is not valid at all. Because it's one of the basic assumptions of the modeling. So of course there are some big amounts of other effects that can also play a role. But I mean the kinetics and the physics inside is quite complicated, so we start like with the basic assumptions and then we see that it works.
I'm afraid we have to move to the next speaker.
Alright.